Okay. So what I intend to do now is to show you a MATLAB simulation of doing decimation. And the concept that the decimation means that first you need to pass the signal through a decimation filter, and then you throw away samples. So I'm taking this an audio signal which I have already stored, and I'm reading this as an audio read function using audio read function of MATLAB into X. It has some sampling frequency f of s. Okay, and then what I do is that I pass it through a filter. We should throw away half of the samples systematically, and then I play both the original voice and the voice which is a decimated voice. So let's do this.
Welcome to DSP1.
This is original voice, okay? And now you will hear a decimated voice.
Welcome to DSP1.
So you see the difference in quality of the two voices. One is played at the original sampling frequency, I think it is around 11 kilohertz, and the second is played at half of the sampling frequency.
Welcome to DSP1.
This is also a decimated version of the voice. So this is important to understand, that what are we trying to achieve here. So this is an important plot. This is the spectrum of the voice, okay? And as you can see, the voice usually have this type of a spectrum where most of the energy is in these frequencies. So this is around sample at around 11 kilohertz. So about 5.5 kilohertz is the pi frequency. So you see the frequency contents in this part of the spectrum, very low energy. So you can, instead of sampling it at 11 kilohertz, you may decide to sample it 11 kilohertz, you may decide to sample it at 5 kilohertz, voice sampling at 5 kilohertz. Or you already have this voice, okay? This is a copy of the spectrum at 0 and 2 pi. And you say, I'll pass it through first pi by 2 filter. This is the pi by 2 filter. That I'll pass it through a pi by 2 filter, and I'll throw away this part of the spectrum. This is once you have thrown away the part of the spectrum. You see this? This is the first operation. And kindly, there is an attendance on poll on CME CC313 digital signal processing on Teams. Mark your attendance. You have till 1 p.m. To mark your attendance on the system. So, this is what happens, that once you pass it through a filter, you clean up the spectrum and then you throw away. And once you throw away, the pi by 2 will go to pi, and this will go to here, and there will be no aliasing, because now the parts which you are closing them together, but after cleaning this spectrum. So this is what will happen. This is the voice in time domain. So voice in time domain and voice in frequency domain is different. This is welcome to DSP1. Welcome to DSP1. So there are pauses. You can clearly see in the voice there is welcome, welcome to. So this is welcome to DSP1. So this is the voice in time domain. These are the two decimated versions of the voice. One is that you are keeping first sample, throwing away second, and this is you are keeping second and throw away first. So it'll hardly make any difference whether you keep first or you keep the second sample. So this is the decimated version of the voice, which says welcome to DSP1, welcome to DSP1. Okay, and you have already seen the spectrum. Let me show you the spectrum again so that you understand what I'm saying here. This is the spectrum. So once you look at the spectrum, you will not find out where is welcome to DSP1. These are the frequency contents in the signal, and the frequency contents are passed through a half pass filter, and this is what you get. Okay, and so this is the spectrum after decimation. Spectrum after decimation. You see that the pi by 2 goes to pi, pi by 2 goes to pi, and this is what you have. Okay.
Welcome to DSP1.
This is original voice. This is original voice. Listen to the decimated voice now.
Welcome to DSP1. Welcome to DSP1. Welcome to DSP1.
So this is the difference in quality of voice, but still you can make out that he's saying welcome to DSP1. So you are not, that concerned. So decimation is to reduce the sampling rate of a signal by a factor of So now we have seen that decimation is primarily you pass it through a pi over d filter, so that you clean up the spectrum before you expand it, means that you're throwing away sample. In case of voice, we have just seen the quality of voice going down, but why you do this? Because you can reduce the cost of the system to half. If you do decimation, you can reduce the cost of the system to half. But for that, you looked at the spectrum. It was welcome to DSP1. Okay, this was the time domain signal. But once you looked at the signal in frequency domain, it was something like this, from 0 to 5 kilohertz. 0 to 5 kilohertz. Welcome to DSP1 was looking like this, and mostly the voice signal will look like this, that most of the energy will be in this part. There is no DC value, and then most energy is in this part, 1 to 2 kilohertz, and then less energy in this part if it is simple voice. And in order, so this is 0 and this is pi once you digitize it. And if you want to decimate, so if you have decided to decimate, you need to pass it through a pi by 2 filter. This is what we have seen, passing voice through a pi by 2 filter. Once you pass voice through a pi by 2 filter, this spectrum will look like this. So spectrum will look like this. You have cleaned up your spectrum. Sorry, this is pi. Okay. You have cleaned up your spectrum from pi by 2 to pi, because once you are throwing away sample, this will be multiplied by 2, and your spectrum, as you have seen, will look like this, 0 to pi. After throwing away sample, you again are going to expand the sample, your signal, and the spectrum will be full spectrum going from 0 to pi once you throw away part of the spectrum. And this you are doing by passing it through first filter and then throwing away sample. You can directly throw away sample then, but then your voice will alias, and this low energy will get into this part of the spectrum and it'll try to disrupt the voice which you really intend to keep. So decimation, we have seen an example of voice in MATLAB. We have seen that you pass it through, how you pass it through a filter. You should design a pi by 2 filter and pass your signal through that filter. Now really one important thing which leads us to polyphase filters is that remember that you have the signal x of n, you design a filter h of n, this is your decimation filter, so you do convolution. You do perform convolution. Convolution, you know the summation, which is h of k x of n minus k y of n. So you do multiplications, additions, and then you throw away half of the samples, right? Now we must ask this question that if I am going to throw away half of the samples, why I am computing them through this very complex convolution summation? Why am I wasting computation on something which I know I will throw away? Would you do that ever? Why would you ever compute something that in next step you are going to throw away? Just wasting computational power, energy, time and everything. Obviously, it does not make any sense. It does not make any sense to compute something which you ultimately the next step you're going to throw away. Okay, in MATLAB we don't mind because it's not a real-time system, but in actual real-time systems we don't want to do this. We don't want to compute something which ultimately I'll throw away. I would rather not compute that. I will only compute what is required to be computed. So I'll not go through the theory of this, but I'll just tell you that in order for not to compute what you are going to throw away, you use polyphase decomposition. It is called polyphase decomposition. Okay, polyphase decomposition. What is polyphase decomposition? That a filter you design h of n, a low pass filter you design h of n, let's say it has 8 coefficient h0, h1, 2, h7, and you intend to use this filter to decimate a signal by a factor of 4. Okay, so a factor of 4 means that is a factor of 4 means that you will keep 1 and throw away 3 samples. Another way of looking at it is that you give this 4 samples and it returns you 1 sample. So this is decimation. Out of every 4 you get 1. Out of every 4 you get 1 sample. But in signal processing, theoretically the way is that first you pass it through this. So every convolution operation will require you to do 8 multiplications and 7 additions, 8 multiplication and 7 addition, and that's what the convolution summation is telling us. And then you keep 1, throw 3, keep 1, throw 3, keep 1, throw 3, and that's what you keep doing. But the polyphase decomposition systematically, there is a mathematical proof to this as well. It systematically helps you to only compute what is actually required to be computed. And how it is done, that you split your signal, your filter into D number. So whatever is the decimation, let's say 4 of 4 filters. How you give first coefficient to this, second, third, 4, then redistribution x5, h6, h7, h8. So you convert a filter into 4 filters by splitting it up into D number of branches. Very simple again, that in polyphase decomposition, a filter is split into D number of filters by giving first sample of the impulse response to the first filter, second, third, fourth, first, second, third, fourth. So you do this. Once you are done by this, then what you do is you give your first sample to this input signal, second, third and fourth. So this is a switch where you are distributing samples. So you are distributing samples. So your first, second, third, fourth, first, second, third, fourth, first, second, third, fourth. So you are distributing samples like this. So you have these samples and you are distributing them to these 4 filters. So 4 samples, and then you make the filter work, and every filter gives you an output. You add all these samples together to get one output. Okay, 4 samples in, 1 sample out. 4 samples in, 1 sample out. 4 samples in, 1 sample out. Let's say that you have this input, a ramp which you want to decimate, your signal is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the filter will work like this. You give 0 input to this, 1, 2 and 3, and then do the convolution. So you get 4 output, add 4 outputs, you get an answer. This is your answer. Then you give 4, 5, 6 and 7. Okay. So if you're doing it in MATLAB, what you can do is you first split your filter into 4 parts, split your signal into 4 parts as well. First part will have first sample, second, third, fourth, first, second, third, fourth. So your signal is divided into 4 parts, your filter is divided into 4 parts, you compute 4 answers. Every answer will have 1/4 size, 1/4, 1/4 ones, and add all of them together and you get an output which will be a decimated output. And that's how you 4 sample in, 1 sample out, 4 sample in, 1 sample out. So this is how you can only compute what is required to be computed, and this is equivalent mathematically. We will not get into the mathematical proof of this, but this is mathematically equivalent to passing a signal through a filter, then throwing away samples. Both are equivalent, but here you are not throwing away samples. Every 4 samples you are computing 1 sample. So perhaps in the next class we will do an example on this so that you understand. So we'll take an example, actually do this in MATLAB or also in MATLAB. The code which we have provided you has this example where filter is divided into 2 parts and signal is divided into 2 parts, and you are shown that the decimation, this and this are equivalent. Same is the case with interpolation. In interpolation you may argue that as we have discussed, that in interpolation first you insert zeros, then you pass it through a pi over L filter. And so you have a signal. Now you have 0, 0, then you have 0, 0, then you have 0, 0. Okay, and then passing it through a filter simply means a convolution. Okay, a convolution, simple means convolution. And convolution, again, you have a filter h of n, and this is a signal which x interpolated n, and convolving means you have h of k xi of n minus k. K goes from 0 to m minus 1. And for the sake of argument, we can again say that why I am multiplying in my convolution summation, there are so many zeros. Zeros multiplied by something is going to be 0, adding it will not change the value if we are just accumulating. So why we are multiplying with so many zeros in my convolution summation? I am just wasting my multiplication. I have this a priori knowledge that many of the samples in the signal are zeros. Zeros multiplying in the convolution summation with the filter coefficients will only result into zeros, and adding 0 into a summation will not change the value of the summation. So I am wasting all these multiplications, which I must not, because a signal processing system, the cost is all about the amount of computation you have to perform, and obviously the storage. So this again does not make any sense, that why we are doing this, and we must not do this. For sure we must not do this. So for the same reason as we were using decimation filters, because we never wanted to compute something which we ultimately are going to throw away. For the same reason, we don't want to multiply numbers with zeros, because we know that this is just useless exercise. So a polyphase decomposition also helps in interpolation. And in this, what we do is same thing. You have a filter, you split that filter into multiple filters. So L number of filters. How? By just splitting the coefficients. We have seen that you give first coefficient to this, second coefficient to this, L minus 1 coefficient to this, then again. So you distribute and you convert your filter into L number of filters by splitting the filter into L branches. Simple, right? Absolutely no problem. A simple MATLAB code can basically help you do this. So would have like H1 colon L colon N will make H0, H1 2 colon L colon N will make the second filter. So MATLAB code is very simple to actually implement this. And then what you do is you copy your signal to every filter. Remember, in interpolation, for one sample we want to generate 4 samples. For every sample, the output will have 4 samples. So you pass your signal to this copy signal, copy signal, copy signal. So now you have a signal coming here, a signal coming here, a signal coming here. So 4 outputs. And then you put a switch here. One sample in, it goes through all the filters and you get L samples out. One sample in, L sample out. You pick this, pick this, pick this, pick this, and you throw this to the next stage. So interpolation in polyphase decomposition is also done in this fashion, where we have a signal, that signal gets in here, and then you primarily do the this picking up sample. So this is the polyphase decomposition for interpolation. So decimation and interpolation plays a very important role in signal processing, and the reason is it does because the reason is that you have to match. There are many applications where you are concerned about the sampling rate, and you are always matching the sampling rate of the signal with something for different reasons, and you got to change the sampling rate usually by an integer factor, but sometimes the application is such that you have to change the sampling rate by a non-integer factor. For example, you are asked that there is a signal or an image, change its sampling rate by 3/2. It's true for the images and as well as for 1D signals, that you are changing, like you have an image and you are just selecting this and changing its size. Okay, all the time you are doing this, right? So it's changing the size of the image to a different size image. So that may not be just a complete multiple, like you are not reducing into half, you are reducing into 1.5 or 1.6 or 1.7 or 1.8. So let's say you are reducing size of the image to 1.8. So 1.8 means 18 divided by 10. So that's how it will be accomplished, that if you're changing size of the image from 1 to 1.8, like you are enlarging this, you are increasing the size of the image, and that's what you intend to do for a reason that you want to make it bigger in look. So here your interpolation is to be done in 2 steps. There is no way for you to directly go to 1.8. The only way for you to do is, first you increase the size by 18, increase the sampling rate by a factor of 18, and then reduce the sampling rate by a factor of 10. So it has to be done in 2 steps. Always we do the interpolation first, because interpolation will not reduce the amount of information. Never do the decimation then interpolation, because if you do the decimation, though you are increasing the size of the image, but you throw away a lot of information, and that'll basically degrade the quality of the image. So never ever do the decimation first. Whenever you are changing the size of the image like this, so you got to do this in 2 steps. One is, first increase the sampling rate by a factor of 18. So how do you increase the sampling rate by a factor of 18? We know this. First, insert zeros. After every sample, 17 zeros. Then pass it through a pi over L filter, right? this will make your image 18 times bigger, though you are not displaying it, okay, because you want to display 1.8. So this will increase the size of the image by a factor of 18. And remember, here you have not like started throwing away samples. Now what you do is throw away samples. But for throwing away sample, first you pass it through a decimation filter, a pi over d filter, and then you throw away. So these two steps will change the size of the image to 1.8. So out of these samples, once you have, for every sample you have 18 sample, then still passing it through a pi by d filter. But obviously sometimes you may argue like putting two filters in cascade does not make any sense, because they multiply in frequency domain. Why not to make one filter out of them? Yes, you can make one filter out of them. And how you do that is by finding out, for example, this is pi over L and this is pi over D. So once you multiply them together, you will be left with only pi over D. So find out which one is smaller, and you pick that. So means whether L is larger or D is larger. So you select one filter. So changing the sampling rate is a very fundamental operation in signal processing, and this is not a big deal. Changing the sampling rate by L over D. How do you change the sampling rate by L over D? First, inserting zeros, then passing it through a filter with L gain and pi over whatever is the maximum of L and D, and then throwing away samples. So these are the two steps which you need to do if you are changing the sampling rate of a signal by L over D. So you got to first increase the sampling rate by L, then pass it through two cascaded filters, an interpolation filter and a decimation filter, but you can combine them into one filter, then throwing away samples. You take an image and image size will reduce. That is the only way to perform it in a manner that you don't lose any information. So whether it is, as I mentioned, an image, which because we understand images better, all the time we are just changing the size of the image and we don't even know what is happening in the background. In the background, if they don't want to lose any information, they are doing this. They are performing an interpolation and decimation all the time. So you are changing the size, they're performing interpolation and decimation all the time to make sure that you get the best quality image. So signal processing plays an important role in making sure that you don't lose any information once you are doing decimation and interpolation. Sometimes it's not in the scope of the course. In communication receivers, like you have a base station and you have a mobile phone, and your let's say base station, your 3G or 4G is telling you that you have we are giving you 4 megabit per second. Okay, and this is how it usually works, that you have a throughput, and the mobile company will tell you that we are providing you 4 megabit per second. Okay, so means in every second your mobile company is transmitting through the base station 4 megabit of information. So every bit of information is coded into a number of samples, okay, like 2 samples, 3 samples per bit. So there is a clock which runs in a base station which has to work at this resolution, 4 megabit and every bit in 4 samples, so 16 mega samples per second, 16 mega samples per 16 at the base station. So there is a clock which is measuring this time, one sample, another sample, another sample, another sample. Then there is a clock in your mobile phone as well, because it has to receive. They got to be synced. This clock and this clock to be synced. Okay. Why? Because instead of 16 mega sample, if you have 16 and 1 mega samples, because this clock is little slower, like 0.00001 slower than this clock, then they will not be synchronized clock, and they'll start throwing some bit. They will get an extra bit after some time, an extra bit, and your mobile phone will not be able to figure out. And not only that, it'll just basically disturb all the synchronization. A sample from the previous bit will get into the next bit, and all kinds of issues will happen, because there is absolutely no way for the crystal which works in the base station to match that crystal with the crystal that is in your mobile phone. Absolutely no way. They are from different vendors. Okay, they have a little, because you cannot exactly make it, no matter how little difference they have. But once you accumulate and something is working all day, so it will result into some extra samples, or it'll eat up some samples. This will eat up some of this sample. If it is if it is faster, it'll eat up. If it is slow, clock is slower, because it's just sampling. It has thrown away 64 million samples, and it is also sampling, but in 1 second, because it has to, once it pass, it got to convert it into analog signal that got to be sampled again here. A sampled signal is converted into analog signal, transmitted in the air, coming to your mobile phone. Your mobile phone has a little different clock, which is 0.0001. So in few seconds it generates another sample. It has absolutely no clue what to do with this sample. Okay, so a very tough problem in the system is that you got to change the sampling rate of the system to match with the sampling rate of the base station. It is a must. An integral component of all communication system is where you got to change the sampling rate in a way that it matches with the sampling rate of the transmitter. We are not using the filters twice. We only put one filter, though in cascade, as I mentioned earlier, you have a pi. The question is about this, that theoretically we got to, it seems as if we have to pass it through one filter, then we have to pass it through another filter, but we combine these two filters together and design one filter, because there is absolutely no use of passing a signal through two cascade filters. Why? Because in frequency domain they multiply. If one has pi over L is bigger than pi over D, then you multiply this with this, left will be this. So it is better you only pass it through this filter. So you pick which filter is a smaller filter, okay, which has less bandwidth, and you only use that. And this is what I have shown here. If you look at this figure, I have said you pass it through just one filter, find out the maximum of L and D. L is the interpolation rate and D is the decimation rate. So you pass it, you design only one filter. Changing the sampling rate, you design only one filter. So MATLAB FIR1 command, I want this lab to be heavily tilted towards interpolation, decimation and polyphase position, so that you understand all intricacies. And I and Dr. Ali will discuss that. Like, you take a signal, insert zeros, plot the spectrum, you take a signal, plot the spectrum, pass it through a decimation filter, plot the spectrum again to visualize that now you have thrown away part of the spectrum, and then only you decimate. So we'll make sure that you do this exercise so that these concepts, because these are very critical core concepts in signal processing, and missing these concepts, you definitely will commit a mistake once you get an opportunity to implement this system in your life. And that means that you intentionally, unintentionally, not knowingly adding noise into your signal, and that will not help you at all in devising algorithms to do the rest of the processing, may it be pattern matching or whatever. So let me just show you this on my screen as well. So this is the concept. This is the concept that you have. So you are changing by L. So you have this filter, which is pi over L filter. Then you have this filter, which is pi over M filter. Then you have decimation. So it is better that you combine these two filters into one filter, which is the maximum of K is maximum of L over M. So this is our system, which changes the sampling rate by a non-integer factor. Okay. And this we have covered, extra copies you get. This we have covered, that you're passing it through a decimation, an interpolation filter. Inserting zeros mean extra copies. And once you pass it through this, you remove the extra copies. So this is what you get. So we have covered this as well. So we know the interpolation, we know the decimation. This is the interpolation of getting extra copies in this. So covered this as well. Okay, you have omega of L, the relationship, which tells us that z raised to the power L, that why the spectrum is, the x-axis is divided by L. So extra copies in interpolation and then passing it to pi over L filter. And this is an example. So, you know, there is a very important concept of polyphase decomposition, which we have just covered. And usually IIR filters are not used for polyphase decomposition, because polyphase decomposition may, I told you that we have a filter. We divide it into 4 filters. One coefficient here, the other here, other here, other here, and then you do this. And this systematically, you are not computing the sample which is not required in your computation. But remember, in IIR filters, you got to use the previous sample. IIR filters to hai ye y of n is equal to a1 y of n minus 1 plus a2 y of n minus 2. So this was a myth that IIR filters, this is the slide which says using an IIR filter in the case has an obvious shortcoming. We cannot take advantage of the fact that we only have to compute only nth output sample. So IIR filters are traditionally not used for decimation and interpolation because the luxury of only computing the sample which you require is not there in an IIR filter, because IIR filter uses the previous sample to compute y of n. So it's an interesting, you know, an incident that I just was teaching the interpolation and decimation, and I taught this slide to students that IIR filters are not used, traditionally not used for interpolation and decimation. And once I came down in my office, there was a person who was sitting there and he was doing his PhD for last 3-4 years, and he was stuck because he was not finding an interesting topic to complete his PhD. So I was just thinking about this, that why IIR filters are not used. Is there any way we can make use of IIR filters? And then I said, let me try, and I took a page and I started figuring out a way to use IIR filters for decimation and interpolation. And perhaps it took me 10 minutes to figure out a way. And I told him, oh, I think I have found a topic for your PhD. So this guy, who is Umar Farooq, then published 2 papers, one using IIR filters for decimation and IIR filters for interpolation, and completed his PhD. So it actually really took 5 minutes to find out a solution, not only a topic, but a solution for PhD. Alhamdulillah, now he has like PhD. This is transformation to implement computationally efficient IIR decimation filters. So elsewhere में उसने publish किया था. So means that once you think that something is not possible and you try that making that impossible possible, and sometimes it happens that you can actually solve a problem which people believe cannot be solved, and sometimes it's such a trivial solution you find for removing that bottleneck or that hurdle. But the decimation, again, polyphase decomposition simply means that taking a filter and splitting it into number of filters and passing a signal through those filters. So this is the decimation. I'll say I'll not get into the technical detail of how this happens, but this is now because in exam you will be asked these type of questions. Though I intend to give you this as a quiz, but I am told that giving you a quiz means that I don't know if you will independently do this or not, but let us discuss this. Rest of the time we have, let us discuss this. This is a signal. Usually you will be asked question like this. You will be given an analog spectrum, not the digital signal, because as I mentioned earlier, digital signal, and we have seen the voice signal as well, has absolutely no information for you to do signal processing. So that's why our interest has always been in plotting the spectrum, the signal in frequency domain. Always interest is plot the signal in frequency domain. So this is the signal with pi over capital T as the maximum frequency content in the signal, and we want you to first sample the signal, the sampling of capital T. Then we want you to insert zeros, L number of zeros. Then we want you to pass it through a pi over L filter. This is the pi over L filter. Then we want you to move its spectrum. Multiplication by an exponential means shifting its spectrum to pi, and then we want you to convert the signal to a continuous signal with a sampling frequency of T by L. So let's try solving this problem. This is a problem from your book. It is 4.38 and gives you a good insight into how the sampling happens and the interpolation happens and the signal processing happens. Okay, so an interesting question where the question is that you have continuous to discrete time converter, then inserting of zeros, then passing of this through a pi over L filter, then shifting the spectrum of the signal at pi of n, multiplying, remember multiplying by an exponential is shift in frequency, and then converting it from discrete to continuous at a sampling rate of T over L, and then this. Okay, so this is a question and you are given a spectrum of, here is the spectrum which is pi by T. This is the spectrum, capital omega. Okay, so if you remember that here is T, mean your sampling rate f of s is 1 over T and your sampling frequency is 2 pi over T. Okay, so you are going to make copies of this at every 2 pi over T. Remember, we have done several examples. Just make copy at every omega of s. So at 0 you have this, at another you have this, you have this. So xi of j omega is a copy at 2 pi by T. This is pi by T, so it's not going to alias at all. Minus, and this will be 1 over T is going to be your amplitude of the spectrum. This is what happens once you do the sampling, right? Step number 1 was this. So you make impulses, copies of the impulses at every 2 pi over t, make copies of the spectrum here, and then multiply your spectrum by t cancels out. So digital spectrum will look like this. So you are here, x of n. So your digital spectrum will look like this at 2 pi, at minus 2 pi, at pi, at minus pi. This is 1 over t. So we know this much. Okay, so we know this much. Then inserting L minus 1 zeros, what will happen? And we know that by closing even our eyes, we can plot this, that L minus 1 copies. So you say, oh, I know no matter what L is, I have a copy, a copy, a copy, and then I have 2 pi and 0. So I am going to get L minus 1 extra copies, and this value will be at pi over L. This will still be 1 over t. And it will happen on the other side as well. So on both sides you are going to see extra copies, 1, 2, 2, minus 2L, 2 pi. So I'm going to see many extra copies, exactly L minus 1 extra copies. So I am done here, and now I am here, which wants to call it V of n. So this is Vi of exponential j omega. Okay? So again, very simple. Sampling means that you make a copy at every omega of s. Interpolation means that you make L minus 1 extra copies between the spectrum from 0 to 2 pi. And this, you just draw this pi over L on your digital spectrum, preferably with red colors, to see what will be left in your signal. So this is what every 2 pi we have copy of every digital signal. So this is with red color. So once you pass it through a filter like this, what will happen? You will be left with this 0, pi over L, minus pi over L, 1 over t. And you will have a copy at 2 pi and a copy at minus 2 pi. Right? So now we are here. And here it wants to call it W of n. So this signal is W exponential j omega. Let me repeat this again. So there is a question, and usually we ask these type of questions in exams and quizzes, that you will be shown a system and something which is drawn like this, which has a continuous to digital converter, inserting zeros, passing it through a filter, moving the spectrum, passing it back to digital. And you are asked to take this in the start of the signal. So this is your x exponential j omega signal. So this is your input signal, exponential j omega, the analog. So you will be given the spectrum, and now you are asked to pass it through the system step by step. So the first step is you pass it through a continuous to discrete time converter with sampling rate 2 pi over capital T. So this pi over T is telling me it will not alias, because pi over T to pi over T copies are here. So do you have copies and this? So this is my xi j omega, still an analog signal with frequency is still omega. We have done several of these. And then I discretize by normalizing my axis, taking away the time. Once I do that, every copy at 2 pi, I get a full-blown Nyquist spectrum. This is my digital spectrum. This is my x exponential j omega. This is a digital spectrum. A digital spectrum will have copies at every 2 pi for sure. Then inserting zeros. Inserting zeros means that I have L minus 1 extra copies. Again, we are not even worrying about what is happening in time domain, inserting zeros, but we know inserting zero means inserting zeros, but this is the spectrum. Then comes this part where you have to pass it through pi over L filter. So if you pass it to pi over L filter, you get this. Pi over L, 2 pi, minus pi. Now you got to shift this spectrum to pi. So this spectrum, once you multiply it exponential j pi over n, will move to pi. This part will move to pi. So after you multiply it with this, and he is saying this is y of n. So a shift in frequency will happen. A shift in frequency will happen. A shift in frequency can be easily plotted. So you will have a spectrum at pi and a spectrum at minus pi. So this is what you are going to see. Okay. So this is what happens once you shift the frequency of the signal. Okay. And you know that this much is pi over L. So pi plus pi over L, pi minus pi over L. So you can figure out what this point is and this point is and this point is. But this is after you make a shift. After you make a shift, okay, so your digital spectrum is looking like this. Actually looking like this, because we are keen to look at our spectrum from minus pi to pi. This is my digital spectrum is looking like. Okay. Now, and this point is pi minus pi over L. L over L mean L minus 1 pi over L. L minus 1 pi over L is my this spectrum. And once now you pass it through a discrete to continuous converter, okay, with the sampling frequency of pi by t by L. Remember what we do? Pi by L, t by L, t by L. So the f of s is L by t. Okay, so you are kind of increasing the sampling rate by L over t. So now here you divide the spectrum by t dash. So the new spectrum will look like this: pi by t dash and minus pi by t dash. So this is going to be your new spectrum, and definitely you are going to pass it through a filter, because there are going to be extra copies, but you are going to keep this copy and you give a gain of a t. So t is now your t over L. So this is 1 over t, t over L. So you have a spectrum which will look like this: 1 over L, pi over t dash, minus pi over t dash. So systematically, moving from left to right, this is what you will be left. So this is pretty much that I intend to cover, but I would still strongly recommend that you please do this yourself as well, and we will give you several assignment questions and maybe a take home or graded quiz, so that you practice it by yourself and you get ready for the exam. Thank you very much. Inshallah, Baki Dr. Ali will take the 1 hour sessions and will make you do practice more. Thank you very much.